Thank you, Nick. Thank you, Daniel. And thank you, all of you guys. Today, I'm going to talk about our recent research about the federated feature selection for horizontal federated learning IoT networks. I'm a PhD student at the University of Bristol and the High Performance Network Group. And I would like to thank my supervisor, Professor Dimitra and Professor Reza. They are the director and the head of the High Performance Network Group, and the Dr. Huan. He will give a presentation later about, and he is a senior research associate in our lab, and we're focusing more on 6G and things like virtual network function deployment and AI orchestration with the federated learning or distributed machine learning. And I'm a PhD student. Now I'm research more like federated learning and Internet of Things. Here are the instructions of this presentation about introduction, proposed algorithms, experiment, results, and conclusion. All right, let's head to the main point. So in the 6G, the big data, we all know that the centralized data are going to be evolved into big data 2.0 to decentralized and the small sized, all of the small sized and decentralized. And with the massive Internet of Things, also we need to penetrate this AI machine learning, artificial intelligence with the intelligence as a service. Also with how to deal with this kind of all non-IID data. And we need to make sure the security of the privacy of the requirements of them. So based on the IEEE guide and some really popular survey paper, there is some basic definition of the federated learning, for example, like as technical trains models and multiple decentralized edge devices. And it seems like it's just like the model is like a horse or it's like a sheep, and the data is like the grass from each farm. So how are we gonna do with decentralized things if we get all of the grass from different places to feed these horses? But now we need to hold these grasses at each point, and then we release this horse to get the grasses to eat it. So that's how we change the data and the model places with the federated learning main point. So with the three categories of the federated learning, I guess all of you guys already know that the horizontal federated learning is the vertical federated learning, and the federated transfer learning based on the overlappings of the samples and feature space. Actually, if they have a large overlapping on the feature space and small overlapping on the sample space, or we can do the horizontal federated learning based on the features. Same idea as the vertical federated learning, vice versa, the federated transfer learning. So here's a question. There's a lot of IoT devices deployed in everywhere. So most of them, their features kind of things like overlapping because we can reuse them, and kind of like environmental, something like temperature or whatever. But the specific use of different features may be different. It's kind of things like that. So how to select the horizontal federated learning features? So these features can represent the whole most kind of performance of this data set, or most kind of attributes of this data set. And second thing is how to find these kind of representative features and divide those features that are not quite important, like in this orange area, and this here, how to pick up. First, we need to pick up these other features which is not important, and then we need to find the important features within this red box, and how to find the overlapping real part of this horizontal part. We can do this. So not all of these samples are labeled. We don't know which features are good or not. So what kind of method we need to use? We need to use the unsupervised methods. So we propose three steps to find these overlapping features. The first step is we propose a feature detection algorithm, which we use the one-class support vector machine, which, the one-class support vector machine, we can flexible define the outliers, what kind of outlier it is, and how much outlier is going to be, how much the marginal distance is going to be, so which can be deal with the non-IID, because each of the data set, they're going to have their own personalized outliers. We don't know, so we can use a one-class support vector machine to define which kind of outliers we need. So we deal with the non-IID problem. And second one, algorithm that we use the feature cluster algorithm. So it's kind of like a hierarchical clustering. We can find which a group of feature is the essential part of the belongs to the overlappings, or which kind of features can represent the whole characteristic of the data set. And the last step is the global federated feature selection. Now we have the optimized feature set of the distributed data sets. All we need to do about these features is do the intersection operation to find the overlapping part. So the advantages of our methods is that first we do the data cleaning and to get those outlier features. And second, we get the insight of this feature relevance. So because, for example, this feature is most relevant to for everyone, every other features in this data set, okay, this feature is outstanding. We can pick up this feature as the feature for federated learning. And the last advantage of our work is that we use unsupervised method. The word is quite tedious, so let's focus on how it's gonna be more vivid. So we use this one-class SVM support vector machine to first detect those outlier features. We use the hyperplane or hyperbole. It's all the same in mathematical sense to divide those outlier features, and then we can see that we inspired from this kind of hot map from the biological things, some kind of different genes from like the UGT or whatever. They can guide some kind of things like proteins or some characteristics of one cells. So we choose these genes as the main point. We choose these important genes, which means we choose the important features of this. And then we do the overlapping. We do the overlapping of the different features we already selected. Now we find the horizontal federated learning features. So here's the system model. There are the kind of different IoT devices, and this kind of thing means that their data set, first we use the one class SVM to divide it and clean the outlier features. And then we use the feature relevance hierarchical clustering to find what kind of features can be grouped together as the main point at the representative feature set. And then we set those features to the federated learning server to do the intersection operation. Now we find this feature overlapping part. At last point, we give the feedback to each IoT devices so they can know what kind of features is important for the horizontal federated learning without leaking any other informations. So we give an insight of this, how to measure the similarity of different features. We use the symmetric uncertainty, which use the information and using mutual information and the entropy of different features. If this symmetric uncertainty is higher, which means that, okay, we already know this feature, what's the uncertainty of other features? How much is uncertainty left? So if the symmetric uncertainty is higher, which means this feature is more valuable. And then we use the average. For example, there are a group of features. We use the average symmetric uncertainty of each feature and then arrange them as a descending order, so we can know which feature is most relevant to others, which features is second relevance to others. then we can get an insight about these features. And also we get the kind of intuitive ideas how to measure these features gonna influence the final label. We use the mutual information stuff to get the information gain of this feature to the final labels, and which will represent as the experiment part. Oops, what's going? Well, it's a yeah. This is a kind of maybe something kind of so whatever is so. After we get the descending order of this feature relevance part, we set as an as a situation as a constraint part to the support vector machine, and with the Lagrange function and also with the KKT condition, we can get the result of this formula. So probably this computer is not like the formula method things. So let's forget about it. So when the support vector on the margin, we use this kind of feature relevance as a diagonal matrix to put it on the samples, and we can see give a weight of it. We can see, okay, if this feature is outstanding, it has more weight. If this feature is not outstanding, it has a less weight. Then when this kind of data sample on the margin, then we find this support vector and use this hyperplane or hyperbole to divide this outlier features and the good features. So let's forget about the tedious algorithm things. So but let's go ahead to the experiment. So we use a full state of our data set to how to evaluate this, how to evaluate the algorithm we propose. We can see we use the boot IoT data set, which has 43 features and 2 classes, and the ACC is the anonymized credit card data set, which has 30 features. And the KDD99 dataset, 41 features, and the DFT IoT dataset, traffic dataset, which has the 100 features. So we can see here is the anomaly feature detection results on the ACC and KDD99 of the each information gain of feature. The above figures is like how this kind of feature average relevance gonna looks like. So for example, in the ACC data set, we can see that different features, they have different feature average relevance, and we can correspondingly see the picture, the C picture. We can see that with the lower feature average relevance, and the information gain of this feature is relatively low, because you can see it's not related with others. It's not quite correspondingly, we're not quite connected to the whole feature expression. And also we can, the same as the KD99, but during our experiments, we find that the feature average relevance is 1. What it means it's relevance to everyone. So what means it's relevance to everyone? This feature's value is all 0, so it can be relevant to everyone. So we pick that as an outlier as well. Then we delete it, and it's exactly the 20 or 21 features in the KD99 data set. So if you're interested, you would like to see that. So after we detect those features, you see these red dot features, we delete about it and mark that outlier features, and the other data of the features we mark as the normal data set. Then we train the 1-class support vector machine, and every data set can define its outlier, the margin, the slack variables, and this is the final results of different 1-class support vector machine. So here the main point of the feature relevance hierarchical clustering. So we can see from the above picture that the feature relevance, we have no idea. But after the hierarchical cluster, like the middle range of this picture, we can see, all right, intuitively, we can cut this tree as kind of different group of features as the main point or the second main point. You can see as the color deep or not, we can see as, okay, these features are more similar with a group of representative features. We can see as this kind of group as the second representative features. Intuitively, more features in one group. This feature group is more representative. Now we pick this feature group as the horizontal federated learning features. And another problem is that how are we gonna cut this hierarchical clustering, like the elbow methods or other methods? Then we find a way called the silhouette coefficient. If you guys are interested in the math, you may see that it can be naturally find how the features gonna group to be. And for example, the optimal number of features, feature groups actually, optimal number of feature groups. For example, we have a group of features, we divide it as 4 groups, 3 groups, or 5 groups. It will automatically decided by us. So with the non-ID, silhouette coefficient, we can see that we give a cluster of 4 features is the same, but with the non-ID, the different features, they have different categories. And here is the non-ID data experiments. We built this data set, and we can see that our feature selection improves the training time of the data set with the horizontal federated learning as the federated average, federated SGD, as well as the after the feature selection, which we call the feature selection for horizontal federated learning. So we use 6-layer multi-layer perception to do our work. So we can see that because of the divergence of different weight, so when the time is non-ID, it is the training accuracy is not quite stable, but with the ID, it's stable. We also calculated the Raspberry Pi's energy consumption with our proposed methods. So we can say after the feature selection, less training time and less energy consumption of it. And maybe in the future, we can do more feature extraction, because extraction is more like do something like PCE, principal component analysis, but selection without changing the features. And also we do some Carroll inference in the complex networks to do the feature insight of data. And the reference is like, thank you, all of guys.
Thank you for the great talk. It was, super relevant to what everyone's doing here on Industry Day.